Alrighty, so we are going to be talking about exponential and logarithmic functions. And while we're talking about the functions, we should also talk about exponential and log rules, like power rules, like adding and subtracting the powers when you're multiplying bases and all that fun stuff. So let's start off by talking about an exponential function. So an exponential function is going to look like this. F of x equals b to the power of x. That's just your basic parent exponential function. Of course, there could be some transformations in there, but this is just the basic parent one. Now, for it to be considered an exponential function, there are two restrictions that we need to consider. One, the base has to be greater than zero, it has to be greater than 0. And I'll explain why in a second. We can't have the negative ones. And then we also cannot have a base of 1. Let's look at those two situations. So first situation, let's consider a negative base, like -2 to the power of x. Not seeing anything graphed, let's look at the table. I'm just gonna do, let me change my table set to automatically do the outputs. Okay, so what's happening is the points should be oscillating between positive and negative. So if we look over at the right side, depending on whatever that power is, whether it's even or odd, your power should be oscillating between positive values and negative values. So that's why it's not actually considered an exponential function. It's not following that typical exponential shape. And then let's say that our base is 1. You just get a horizontal line because no matter what that power is, you're going to get a 1 in there as your output. All right. So some properties is that the domain for our exponential function, we put in a normal exponential function of just 2 to the power of x. It's going to be all real numbers. You can literally put any x value into that function and get an output. And then the range, that is just positive outputs. There's a horizontal asymptote at 0 and nothing below that x-axis. All right, so then when b is greater than 1, as you just saw in our graph, I put a 2 there, your function is increasing. Like this. And then if b is a value between 0 and 1, like 1/2. So think about what happens when you multiply 1/2 by itself multiple times. The values get smaller and smaller. So that would be a decreasing graph. All right, so that is a few basics about our exponential functions. Right now, I want to look at exponent rules for a quick second. So first rule is if we have a 0 as our exponent, anything raised to the 0 power is going to be 1. The thing that you have to pay attention to is what is the 0 on? If it's just on, like right here, we have x to the 0. If it's just on that variable, only that thing is turning into a 1. So that 2, still a 2. It'd just be like a 2 times a 1. Now in the next situation, we have both the entire quantity 2x being raised to the power of 0. So everything turns into a 1 there. Then we have our products. So if you were multiplying the same base, you add their exponents. So like 2 to the power of 2 times 2 to the power of 3, I would add their exponents. And you would do that even if the power is negative. If you are multiplying those bases, you add the exponents. Now, quotients, if we are dividing the same base, we subtract their exponents. And again, I don't care what the sign is. Even if I had, let's say, x to the -3 over x to the -4, that would be x minus 3 minus -4. That would be x to the power of 1. And even if that was a positive 4, that would be -7. So no matter what, you're just going to subtract those powers and the x ends up in its like numerator spot. You can deal with the negative power later, but just to get started, you subtract your powers. A little bit bigger. Okay, next property, negative exponents. So like what I was just saying, if we happen to, well, let me write that back up again. I shouldn't have erased it. If I happen to end up with a negative exponent and I want to turn it into a positive exponent, essentially what this is showing me here is that in order to get a positive exponent, you just put the base in the opposite part of the fraction. So looking over at my example over here, I have a -3 on my y. So in order to make that a positive 3, I just put the y in the denominator. And then I also have a negative exponent on my z that's in the denominator. So to make that a positive 1, I put that z up into the numerator. All right, power to a power. Technically, you do not apply powers to powers. You multiply them. So if it looks like you have a power on a power, like in this situation, you would literally just multiply those powers together. And then last thing, roots. We can rewrite exponential expressions that have fractions in their power as roots. So pretty favorite one is the 27 to the 2/3 power. Whatever value is in the denominator, that's what kind of root you have. So since I have a 3 in my denominator in the power, that would become a cubic root. You can kind of think about it as that numerator is the top dog, so it actually gets to stay in the power. It doesn't have to move. Okay, so I want you to go ahead and pause the video, and I want you to do practice 1 on the next page. When you are done practicing those, go ahead and unpause and watch the solutions. Okay. So there's a few ways that I can deal with this, but I think the first thing that I want to do with part A is make that a positive power. So I'll make that a 1/16 to the positive 1/2 power. And then I see a fractional power, so I'm going to rewrite that as a root. That would be 1/, that'd be a square root. And then 16 would be to the first power. Not that I need to write the square there or write the 1, since those are both things that we don't typically write in. Like we don't write powers of 1 and we don't write the 2 in the index for square roots. I'm gonna write it anyway. And then simplify one step further. The square root of 16 is 4. All right, next one. I see that I have 4s being multiplied together. So instead of dealing with that negative power right now, I am just going to multiply my bases by adding my powers. So 16 plus -18, that is -2. Now I'm going to deal with that negative power by putting the 4 in the denominator. 4 squared is 16, so this simplifies to 1/16. All right, last one. I have division, but those are not the same bases. but I know that 9 is actually 3 squared. So I think I'm going to go backwards in the simplification process really quick. I'm going to rewrite 9 cubed as 3 squared cubed. And then just leave the 3 to the 7 alone. All right, now I have a power to a power, so I multiply those powers. That'll be 3 to the 6th over 3 to the 7th. I have the same base being divided, so I'll go ahead and subtract the powers, which gives me a 3 to the negative 1. To make that a positive 1, I'll put that 3 in the denominator. I'll put the 3 in the denominator. And you can write the positive power of 1, but I'm going to skip it. Really quick, what I want you to take out of this is if you need the structure of writing up the rules, like if you need the structure of going from 3 to the 6 over 3 to the 7 and then actually showing the subtraction of the powers, do it. But if you can simplify those on your own and just know that that's going to be 1/3, you do not need to write out all those steps. Use the rules when you need to see the structure, you forget what to do. But if you see these and you can simplify them right off the bat, I don't need to see you write all these rules down. They're there to help you when you forget what to do. All right, practice 2. Solving exponential equations. There's a few different strategies that we can use to solve exponential equations. For something like problem A, what I'm going to do is I see that my variable is in my base. So I'm going to try to get the powers to be the same so that I can just drop the powers, which I can do. I'm going to rewrite that 5 to the 6th as 5 squared to the 3rd power, because technically 2 times 3 will get me that 6. And with having that 3 kind of on the outside, I can drop those powers of 3, kind of essentially canceling them out. In solving the equation, b equals 5 squared, or 25, sounds a lot easier. It's something I could do without my calculator. All right. For problem B, I'm going to show you 2 options. The first option, you can do it similarly to what we just did. Get the same base and drop. Yeah, get the same base and drop them. Just like in part A, we got the same power and dropped the power. So I would like you to try that method and pause the video really quick. When you're done, go ahead and unpause it. I'll go through that solution and then show you the other technique. Okay, so option 1, I am going to go ahead and try to get the same base on both sides. I have 7 to the 1 plus t. That's what I'm ideally trying to do, is get a base of 7. In order to get a base of 7 on the other side, I'm going to have to make my power negative. So I'll make that a 7 in the numerator, but then I'll make the power the opposite sign. All right, so now since my bases are the same, I can go ahead and essentially cancel them out and solve for my powers. All right, so t equals negative 1/3. Next. All right, second option. I am going to show you guys this method because sometimes there's going to be some equations where you can't necessarily drop the bases or drop the powers. So I'm going to restructure our equation so that we only have one exponential. So I'm actually going to start off with my 7, 1 plus t whole 7 to the negative 2t. And I'm going to go ahead and, oh, you know what? No, I'm not even going to start off with that, because what if we didn't think to do that in the first place? What I'm going to do is I'm going to take that 2t power from the outside and I'm going to distribute it to the inside. So raising 1 to any power is still going to result in 1. But when I distribute that 2t to the denominator, it's going to stick to that 7. So I'm going to go ahead and get my exponentials on the same side really quick. This is not your typical solving process. This is just to kind of get this in the form so that I have only one exponential and you can see a different technique. All right, so to get my exponentials only on one side, I'm going to go ahead and multiply that 7 to the 2t to the right. Hey, I'm multiplying by the same base. What do I do with the powers? Add that. So that'll be 2t plus 1 plus t, so 3t plus 1. All right, and then here we go. This is the solving technique that I wanted to show you. If you're ever in a situation where you're solving an exponential equation and there's only one exponential and you can't get the same base, can't get the same powers, here's what you do. Convert it into log form. So always start with your base. This is going to be a log base 7 of 1 equals 3t plus 1. Now, any log with a 1 on the inside is going to actually be 0. Log of 1 just is 0 no matter that base. Sorry about that, guys. But if you forgot, you could always put that in your calculator. Let me show you. Math. Go down to the bottom, log base 7 of 1 is 0. And then just solving for t. You get that negative 1/3, just like we did for the other technique of solving. So that's it. Let's move on to logarithms. If you have any questions, make sure you're writing them down. Okay, so logarithmic functions. Your basic parent logarithmic function is going to be in the form sorry about that. F of x equals log base b of x. Where again, same restrictions as before, b has to be greater than 0 and not equal to 1. All right, so properties for our log function. So log base b is going to be the inverse of b to the x. Natural log and e. The domain of b to the x is greater than 0. And the range of b to the x is all real numbers. We talked about that on the front. Wait. We shouldn't be talking about b to the x, we should be talking about log. So hold on. If the domain of b to the x is greater than 0, what in the world did I write on my cheat sheet? I had the right lines, I just have the wrong function. Whoops. So let's think about that really quick. Domain of b to the x is all real numbers, so that would be the range of log base b. And then if the range of b to the x is y is greater than 0, that'll be the domain of log base b. All right, last few here. Log base e is the natural log, and we write that as ln of x. And then log base 10 is the common log, and we just don't write the base. All right, last two things. So when b is greater than 0, just like last time, our graph is increasing. But it's increasing in a different way. It'll be increasing like this. And then if b is between 0 and 1, the graph is decreasing. So like this. Don't believe me? Let's take a look. All right, math. Okay. I'm pretty sure you guys believe me for the increasing, but let's do like 0.5 as the base for decreasing. There you go. All right. Last few things. Let's talk about log rules. All right, so log property. If you have a log of 1, like we talked about before, whether that's natural log, any other log with any different base, you're going to get an output of 0. If you are taking log base b of b, remember logs cancel with exponentials, and technically 1 is the power on that b there. So you'll just be left with a 1, which will take me down to the powers later on. Okay, actually I'll look at that. Products. If you have multiplication going on inside of your log, you can take those factors that are being multiplied in the log and separate them into their own logs with addition in between. And then if you have division inside of your log, anything that's in that denominator, you can put inside of its own log with a subtraction in front of it. And that's actually playing off of the next rule that I'm going to go over, but let's just look at these examples really quick. So looking at this example, all the logs that are positive are 7 and the y. So those would both be in the numerator together. And then the 6 and the x, those both are negative logs. So I would put those both in the denominator when I combine my logs together. All right, so that was the product and quotient properties. Let's look at the power property. I know I've mentioned this a few times before. So if we have a power inside of a log, applied to everything inside of the log, just to be clear, we can expand that log by taking that power and putting it on the outside as a coefficient. So if you notice, we basically have addition and multiplication going together, subtraction and division, and then powers and multiplication going on together. All right. Moving on to the last two here. Reciprocals. I'm going to show you the example first and talk about why this works. So over here, I have log base 2 of 1/3. If I want to put that 3 in the numerator, I can make that a 3 to the -1. Because right now it has a +1 as a power. If I put it in the numerator, that'll make it a -1. Okay, I have a power inside of my log. Let me take that power and apply it to the outside. So then I have a -1 on the outside, or just a negative. So essentially, looking from the beginning to the end, if you have just 1 over something inside of your log, you can take that something in the denominator, write it normally, and put a negative in front of your log. All right, and then last one, change of base. This is especially helpful if you have an older calculator that does not have that log base button. So if you need to evaluate a log, let's say you need to evaluate log base 15 of 4, but you don't have that log base button. The way you have to type that into your calculator is using the common log or the natural log. So I would type in my calculator log of that X value in my numerator divided by log of that base in my denominator. Typically, we just let that new base, the new M, be 10 or E. That way we can just use our common log or our natural log, which is why I have these two set equivalent to each other over there. And even if I wanted to graph that, like, let me go show you my graph here. If I did not have that log base button, in order to graph that function, I would do log of X, since that's inside of my function, it's the bigger thing that we see, divided by log of 0.5. You put your base in your basement, and you can see how those are the same graph. All right, so let's go ahead and look at practice 3. All right, so practice 3, it says evaluate. So in order to do this without a calculator, I'm going to have to rewrite this as much as possible. I would like you to try to tackle this and try it on your own. When you're done, unpause the video, watch through my solution. All right, so I'm going to rewrite that E with a power instead of a root. I think that'll be easier to deal with. And then instead of having that E in the denominator, I'm going to put it into the numerator. And in order to put that E into the numerator, I have to make the power the opposite sign. All right, now I know ln and E are inverses of one another because that ln is technically log base E. So I'm going to cancel them out. And I am left with 1/2, or I'm sorry, negative 1/2. All right, next one. Let's see. I see that I have log base 7s, and then I have 7s inside of both of my logs. So what I'm going to try to do is get them in a form where I can cancel the log base 7 with the exponential base 7, which I could do right now. I can cancel the first one out and make that a 10 times 3. I'm left with the 3 right there. In my other one, though, I'm going to have to rewrite that 7 or that square root of 7 in exponential form. So that would be 7 to the 1/2 power. Cancel out log 7 with the exponential base 7, and I'm left with 1/2. So that is 30 minus 4 times 1/2, which is 30 minus 2, which is 28. Next. Okay, last one, practice 4. The bacteria population in a bottle at time t has size at function. So it's changing over time at an exponential rate. After how many hours will there be 5,000 bacteria? So I'm going to put 5,000 in for P of t since that's representing how many bacteria I have. And I want you to try to solve for t. Try it on your own before you continue watching, but I'm going to go ahead and start the solution right now. All right, so typically when you are solving an exponential equation, like I said before, we either try to get the same base and cancel them out, get the same power and cancel them out, or we turn it into log form. I'm going to turn this into log form because my power is in the, or my variable's in the power, and if I use if I turn this into log form, it will no longer be in the power. Before I can do that though, I need to get the exponential by itself. So that would be 5 equals e to the 0.35t. Now I can go ahead and put that into log form. All right, so that would be log base e of 5 equals 0.35t. Okay, so really that's natural log of 5 equals 0.35t. I'm going to go ahead and divide by 0.35 and put that in my calculator. All right, so 4.59. Let's go for 4.6. Let's just do 4.6. And what was our label? Is that minutes, hours? Hours. T is measured in hours. All right, so that is it. Thank you for watching the notes, and make sure if you have any questions, you ask them in class when I see you next.